vaporization and vapor pressure. And we've talked about this transition between a liquid and a gas. You heat up the water and it will evaporate or vaporize. It happens faster at a high temperature than at a low temperature. So we're going to look at exactly what's going on here. So here we have an illustration of water molecules in a beaker, and these molecules are moving. And they're moving around, they're swimming around. They have an average kinetic energy, but an average is just an average. There's higher and lower. So some of these molecules are moving faster and some are moving slower. They all have these attractive forces, hydrogen bonding, etc., that are holding them together. If you get a molecule at the surface, it's not necessarily just going to fly off into space because it's being attracted by the other water molecules, right? But if one of those molecules at the surface has a higher kinetic energy, it's moving faster, it could break away and go off into the gas state. It could break free. Does water evaporate at room temperature? Yeah, it does. So, I mean, you spill a cup of water and you come back, the counter was wet, and you come back an hour later and it's probably dried up, right? Where'd the water go? Somebody, mysterious elf, come and wipe it up for you? I've been waiting for the cleaning elves to come visit my house for decades. It's not happening. So I think of this as being like a game of Red Rover. You guys know what Red Rover is? Yeah, they don't let kids play that in school anymore because somebody might get hurt. Kids can't have any fun anymore. So if you don't know, Red Rover is you get two groups of kids in a big field. And the kids hold hands, which could be gross or exciting, depending. But you're holding hands, two lines on opposite sides of the field, right? And then somebody in one group says, Red Rover, send Sally right over. And so Sally from the other side comes running across the field towards this line of people holding hands, and she's trying to break through your hands, right? So that's a little bit how I see this going on here. So we have these water molecules at the surface. They're holding hands with each other. These hydrogen bonds, they're attracted to each other. And you've got some renegade water molecule in here that's moving towards the surface. If it is moving fast enough, it can break through the Red Rover line. So if Sally comes just kind of ambling over and walks and just kind of bumps up against your hands, is she going to break through? No. What if she's racing as fast as she can? She may or may not. It depends on how strong those people are that are holding hands, right? And if you're a smart Red Rover player, you know who's got a weak grip, and you're going to go for them instead of the strong kids, right? So if you can break through, if you have enough momentum, enough energy, you can break through and escape. So these water molecules got through the Red Rover line. I forget who this quote was by, but describing water molecules, it's a wild dance floor there at the molecular level. So think of this as like a mosh pit or something. It's people just all over the place. So vaporization is the transition from a liquid to a gas, and then the opposite of condensation, going from a gas back to a liquid. So what if this water molecule is in the gas state? What do gas particles do? They travel in curlicue lines? Straight lines. They travel in straight lines until they hit something, right? So here's a water molecule that happened to be just coming straight down. What's going to happen when it hits the surface of the water? It's going to go back in. It's going to get stuck, right? You can't break through the rover line and escape if you're going back in. Only the ones that are going out can escape. So that would be condensation. Evaporation is when it leaves the liquid and goes out. So here's a graph of showing the distribution of thermal energy. So the fraction of molecules with a particular energy, and here's the increasing amount of energy. So we've got like 0 particles that have no energy at all. And as we look to higher and higher energies, we see more and more particles have that temperature. And then as we keep going up, we see the number of particles decreasing. So it's a kind of a bell curve there. So here would be maybe the average temperature, the average kinetic energy at a given temperature. When you increase the temperature, you're increasing the average kinetic energy of the molecules, right? So the average goes up. This whole curve shifts to higher kinetic energy at a higher temperature. It also spreads out, though. The curve broadens out. And so if we look at this dashed line here as the minimum kinetic energy needed to escape the liquid, we see the area under each of these curves would be the fraction of molecules that have enough energy to escape. So this is how fast you need to be running to get through the red rover line. And this would be the number of people who can run that fast to get through. At a higher temperature, more of the molecules are able to get through. So at high temperatures, vaporization occurs more quickly. Our clothes dryer is currently broken. It's a real bummer. So I can put a wet towel in the dryer and turn it on, and it will tumble and tumble and tumble, but it doesn't heat. When it works, it gets hot in there. Why do we have the dryer get hot? To make the evaporation process go faster, right? It takes a really long time in a room temperature dryer to get that towel dry. So, of course, we don't even bother. But you get the idea, right? Things evaporate, things dry faster at higher temperature because more of the particles have enough energy to escape. That's why hand dryers give you warm air in the bathroom to help dry your hands. Any questions?
Mine just pushes the air. I don't usually feel like that hot.
Well, some of them aren't that hot. There's the accelerator ones that just like gale force winds, right? And it's funny because it makes your skin do all weird things. Yeah, they're kind of weird. They don't have as much heat. They're really more about moving the particles that do evaporate away. If you had both going on, it would be even faster. Yeah.
So I saw this one video, something separate from this, but it was this guy, he was standing outside and it was like super cold and he had a pot of boiling water and he threw it like out in the air and it instantly turned into like snow. So how does that happen?
I've actually done that.
Yeah?
Yeah. So the last time I was home for Christmas, it's depressingly a long time ago. My parents live in Minnesota. The high that day was minus 12. Right? That was the high. So later in the evening, because we had heard about this, so we boiled a pot of water. And when we went outside in the front yard, and we threw it in the air, boiling water, throw it in the air, frozen by the time it comes back down. It's just insane to see. So there's actually something too complicated I can't actually explain to you that has to do with momentum of temperature change. And that happens because the water was so hot when it started, it doesn't work as well with like room temperature water, that's not what you would think, right? You would think, well, if the water's already cold to start with, it would freeze faster. But there's some weird momentum thing going with the temperature change that I really can't explain to you. But it does work. It does work. Very cool. Literally, it was hot and it was cool. And if that hadn't been, before the days of cell phones, I would have a video to show you. But we didn't have cell phones back then. So heating something can cause vaporization to occur faster. Another way to increase the rate of vaporization is to increase the surface area. So think about that beaker of water, right? In order for a water molecule to escape, it has to get to the surface. If the surface area is small, there's only a few particles that can actually get to the surface. If you make the surface area larger, now you have a lot of particles that have access to the surface. So think about this. 2 cups of water, leave one sitting on the counter, spill the other one on the floor. Come back later. Which one's more likely to have completely evaporated? The one on the floor or the one still in the cup? The one on the floor. It got all spread out. The surface area was increased dramatically. So it's going to evaporate more quickly than water just still sitting in the cup.
That's because it takes off the top layer, right?
Yeah, in order for, because go back to this. Yeah, you missed that part. It's okay. Oh, Dosari, I love you and I hate you. There we go. So in order for the molecules to escape, they have to actually get to the surface. If the surface is small, we got all of these guys down here, they just don't have any access to the surface. You make the surface a lot larger, a larger fraction of the molecules have access to the surface, they have the possibility of evaporating. And so in the bathroom with those hand dryers, right, it says to rub your hands, right? You want to spread the water around and increase the surface area so that it can evaporate more quickly. We see that liquids with strong intermolecular forces evaporate more slowly. So again, with the Red Rover line, let's think about 2 games of Red Rover. One is kindergartners, and one is the linebackers on the Fresno City football team. Okay, so you are going to go and play Red Rover in both of these games. Which one are you more easily going to get through the line? The kindergartners or the football players? This is not even worth asking. The kindergartners, right? You get through their line very easily. Why? Because they're little kids. Their grips are weak, right? You don't have to be moving very fast to get through. The football players, you're going to have a hard time getting through, right? Because they're holding tightly to each other. They're stronger. So stronger intermolecular forces, it's a lot harder to get through. It's harder for the molecules to escape. They have to have a much higher energy in order to break through. So you think about maybe the football players playing with, a game of Red Rover, and in order to get through that line, you want to be moving fast. And if you're a big guy moving fast, you've got more kinetic energy, you're more likely to get through. If you're moving slowly, you have less kinetic energy, you're less likely to break free. So strong intermolecular forces, slow evaporation. So here's a word we've seen before, volatile. Volatile means a liquid that vaporizes easily. Now this is a qualitative term, it's a relative term. Non-volatile is a liquid that does not vaporize easily. So alcohol is considered volatile. You go to get an immunization and they wipe your skin with alcohol and it just evaporates so quickly, right? But if you get like vegetable oil on your hand, wait for an awfully long time, that's just not going to evaporate, right? The dog's going to come lick it off before it evaporates. So vaporization involves transfer of energy. So if we think about that beaker that we had the picture of, and we think about if it's thermally insulated, so it's not going to be able to absorb or release heat to the surroundings, as the molecules evaporate, what's going to happen to the temperature of the water? I got a vote for slightly increase. What are the other 2 options? Decrease or nothing happens, right? Well, let's think about it. Which are the molecules that are able to escape? High energy molecules or low energy? The high energy molecules, right? So we've got all the high energy molecules that are escaping. What does that do to the average energy of the remaining particles? It decreases it. Lower average thermal energy is a lower temperature. So when water evaporates, it cools. This is why when you're sweating, it cools you down. That's why your body sweats, is to cool you down. Because as the sweat evaporates off your skin, it is taking heat away from your skin and helping you to cool down. So vaporization is an endothermic process. You have to put energy into it to cause it to evaporate. And so if you think about boiling water, what's the fastest way to cause vaporization? Well, heat it really high and get it boiling, right? So you heat the water, it evaporates faster. That tells me that this is an endothermic process. I'm putting heat into it. So that's not too hard to remember. What is a little confusing is that the opposite, condensation, is exothermic. I'm having troubles with Doceri here. It's waiting for the screen. Does that picture look like my picture? No. I don't know what's going on with it. But your screen still works, so cool.
So it releases heat that
Yeah.
actually form.
Yeah, when water condenses, it actually releases energy. That just doesn't seem right, does it? Have you ever gotten a steam burn? No, that's good because it's not pleasant. So imagine pot of boiling water, right? Do you want to hold your hand over the boiling water? No. Because the steam that's coming up, when it hits your hand that is cooler, it will condense on your hand and it releases energy, releases heat, and can cause a pretty severe burn. It's not that the air above the pot is hot, it's that the steam condensing on your hand releases so much energy. Here's a graph I made comparing average daily temperatures in July from 71 to 2000. I just pulled this off the internet. For Fresno and for San Francisco. Okay, we are, roughly the same distance from the equator. So it's not that San Francisco is so much farther north that they're cooler. The average high in Fresno in July, 96.6. The average low in San Francisco, the average high in San Francisco, 68. That sounds nice, doesn't it? The average low in Fresno, 66. The average low in San Francisco, 54. So it's much cooler in San Francisco in July, we know that. What's really interesting to me is that the difference between the high and the low in the Fresno area, 30 degrees. And we know this. It could be 60 degrees, the coolest part of the night, and it could be 100 degrees at 4 o'clock in the afternoon. These huge temperatures, I lost my word. Swings, that's what it is, huge temperature swings. That's why no matter what you wear, during part of the day you're going to be uncomfortable. You're either going to be warm or you're going to be cold. And so we just wear what we feel like wearing, right? In San Francisco, the difference is only about 14 degrees. Why? It's the water. San Francisco is surrounded by the ocean and the San Francisco Bay. So what happens is the sun beats down during the day. Well, it heats up the land, it heats up the air. As it hits the water absorbs the energy and it increases in temperature, but water has a very high specific heat capacity, and so it only goes up in temperature a little bit. Then the sun goes down and that source of energy goes away. The air cools, but now all this water is going to release energy back into the environment. And so the water moderates the temperature. Here in Fresno, it's a very arid climate, and so there's not a lot of water around here to moderate the temperature. And when we do have those occasional weeks in the summer where it just doesn't cool down at night, you look at the humidity, and the humidity is higher than it normally is, and that's what's causing the temperature to not cool down. Any questions?
Did your kids ever ask you about stuff like the steam burn thing, and you were like, oh, it's because of that?
My kids do ask me questions about stuff, and I do give them scientific explanations. Yeah. I'm raising some nerds, and so far I've got 2 working on graduate degrees in chemistry, and the third one is planning to major in chemistry when he goes to college next year. We're not forcing them to do that. I don't know. It's just, I think it's genetic. You got two parents that are chemists, there's just no hope for you. Okay, so there's energy involved in evaporation and condensation. So the heat or enthalpy, remember that funky word? The heat of vaporization, so we call it delta H vap. That's the change in enthalpy due to vaporization. The amount of heat required to vaporize 1 mole of a liquid at its normal boiling point. So for water, the heat of vaporization is 40.7 kilojoules per mole. So to vaporize 1 mole of water, 40.7 kilojoules. The heat of vaporization is always positive because to cause something to go from a liquid to a gas, you have to put energy into it. It's an endothermic process. It depends a little bit on temperature, but not nearly as much as you would think. So here we have a table from your textbook. And again, heats of vaporization are not something that you should memorize. So here we're looking at water. Where's my pointer? It's messing up. Anyway, look at the water. Heat of vaporization at the boiling point is 40.7. At room temperature, it's 44 kilojoules per mole. A little bit higher, but not much. And then there's rubbing alcohol, acetone, and diethyl ether. And we see that the heats of vaporization for those substances are lower than for water. Okay, so we've rebooted the computer, we've reconnected everything. Hopefully this will be okay now. Don't flash at me like that. So, yeah. Vaporization is endothermic. You have to put energy in.
Whoa.
Right. Good grief. Okay? Good grief. When a substance condenses, condensation is the opposite of evaporation. So if evaporation is endothermic, condensation has to be exothermic. So when water in the gas state condenses into a liquid, it releases energy. It's the same amount of energy that it absorbed when it evaporated. So the number's the same, the sign is different. Again, the sign on energies is just which direction is the energy moving. We can use the heat of vaporization as a conversion factor between moles of the substance and amount of heat involved in the vaporization or condensation. So let's do that. Calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. So this is a type of problem you're going to have to be able to do. Do you need to know the heat of vaporization? No. You need to know how to use it. So don't memorize heats of vaporization. On an exam, I'll give them to you. So we're talking about water, vaporizing it at its boiling point. That's what the problem said. And so we're going to use this 40.7 kilojoules per mole. So I'll go back to the problem. And let's write this down. The heat of vaporization is 40.7 kilojoules over moles. Yeah, so we need to do some other unit conversions here, right? Because we're given kilograms and we're asked to find kilojoules. So this is a conversion factor relating kilojoules and moles. And if we had moles of water, that would just be apply the conversion factor and be done. But we're starting here with kilograms. So we're starting with kilograms, and we want to end up with kilojoules. This gives us moles to kilojoules. So we have to find moles of water. So we're going to take kilograms to grams and then to moles. It's just a dimensional analysis problem. So 2.58 kilograms of water. And then we want grams here, and we want moles here, and we want kilojoules here. Put the moles in so they cancel out. grams, kilograms. Get all the units in there first. The units tell you, do we multiply, do we divide? Where do we put the numbers? The units help you out. Write them down. Some of you still are just putting numbers in. When you just put numbers in without units, it's really easy to put them in the wrong place. So relationship between grams and kilograms, we just need to know what kilo means. Hopefully we're all good with that by now. Kilo means 10 to the 3. So instead of writing kilo, I'll write 10 to the 3. So 1 times 10 to the 3rd grams is equal to 1 kilogram. Moles to grams, that's the molar mass. So the molar mass of water is 18.02 grams to 1 mole. And then this is the new one, it's just this heat of vaporization, 40.7 kilojoules per mole. So we take, and do the math, 2.58 times 1 EE3 divided by 18.02 times 40.7. So 5827.19. How many significant figures should I have in my final answer? 3. This number was given with 3 sig figs, and the heat of vaporization was given with 3 sig figs. So be careful when you round that. It's 5,827. That would round to 5,830 kilojoules. Or safer to put it in scientific notation, 5.83 times 10 to the 3rd kilojoules. Any questions? We'll save the rest of this for next week.